average was 74.1, so much better than last time. Standard deviation 19.6. The high was 100, and there were 3 of them. So let's go through it. You're asked here first to state the Lewis and Randolph rule. Importantly here, identifying the variables as it would apply to component 2 in a solution, and give an example of a situation in which it would be valid. Well, the Lewis rule you're asked to do it for a solution here, so that means we're talking about a liquid phase. So the fugacity here of the component 2 in the solution is equal to the mole fraction times the fugacity of the corresponding pure component 2. And it's important that you identify all of those. And it should hold that component 2 is present in excess. That's the most common one, but there are other reasons. If the solution is in fact made up of molecules that are so close in their nature to one another that they form an ideal solution, that would be another example. Secondly, you were asked, why are the Wilson equations preferred over the Margulis and Van Laar equations for correlating isobaric, that is, constant pressure VLE data? Well, these kinds of data show a variation in temperature as we cross the composition range, and the Wilson parameters have a built-in temperature dependence to them, so they can account for that, whereas the Van Laar-Margulis equations tacitly assume that the activity coefficients are independent of temperature. State the definition of the dew point temperature, dT of a VLE system. That's the temperature at which pertains to a vapor phase, and it's the temperature at which the first drop of condensate or dew starts to form. Okay, next we got a solution of components 1 and 2 in which the mole fraction of component 1 is 0.4. The partial molar volumes are given here. And you have, first of all, to calculate the molar volume of the solution of 1 and 2 in which the mole fraction of component 1 is 0.4. So we put it together like this, put in the numbers, we get 41.68, per mole. Secondly, if the pure component molar volumes are 33 and 48.8 cubic centimeters per mole respectively, calculate the molar volume change of mixing at a mole fraction here of 0.4. Well, if you calculate that molar volume change of mixing is equal to the volume of the mixture minus the volume that would be occupied by the corresponding amounts of pure components. That works out to look like this. We put in the numbers, we get minus 0.76 cubic centimeters per mole for that. Next you're asked, considering air to be a mixture of 22 mole% oxygen, 78 mole% nitrogen, calculate the minimum amount of work required. And I give you here, I wasn't going to give it to you at first, but because you should know that, is delta G for the process to separate it into its pure components at 300 K and 1 bar. Assume ideal gas behavior. Although under these conditions, you would probably not have to be told that, you would know to assume it. Well, the molar Gibbs free energy change for demixing would be just minus that for mixing, and the expression for the molar Gibbs free energy of mixing is given here. So it's a matter of plugging in the numbers, and we end up with 1314 joules per mole. We know it has to be positive because you're going to have to do work in order to get these components separated. Okay. Next, pure carbon dioxide gas at 291.2 K has a second virial coefficient of minus 130.8 cubic centimeters per mole. That's a hint that we're not going to be able to treat the gas phase as an ideal gas. If carbon dioxide gas at a pressure of 20 bar and a temperature of 291.2 is put in contact with ethanol, its mole fraction is found to be 0.0138. Determine the value of Henry's constant at 291.2 K. This is a picture of the situation, and we've got a gas here. It's at 20 bar, so not surprisingly, it isn't quite an ideal gas. And you were given information to describe it by virtue of being given the second virial coefficient for it. So Henry's law in its general form here is written as the fugacity of the component here in the gas phase is equal to small fraction times Henry's constant, and mole fraction of the liquid phase times Henry's constant. So now we need to evaluate that, and the fugacity of a pure gas is given conveniently here as just the pressure modified by the factor, which is the exponential of second virial coefficient times P over RT. Put in the numbers for that, we get a fugacity in the gas phase of 17.952 bar, from which we can calculate Henry's constant as 1301 bar. Next, we've got a pair of liquids 1 and 2 forming a solution at 40 degrees C, for which the log of the log of the activity coefficient for component 1 is 0.68 x2 squared. That would be all I really need to give you, because then you know automatically that log gamma 2 would be 0.68 times x1 squared. Pure component vapor pressures are given at the temperature of interest here. And you're told that an azeotrope exists if there's a value of x1 lying between 0 and 1 where the relative volatility is equal to 1. In fact, that would be the way you would find it. You would be just set the relative volatility equal to 1 and then solve back for that mole fraction. But I asked you instead to show that an azeotrope actually does exist here at a mole fraction of 0.7. And that just means writing the expression here with the modified Raoult's law for the relative volatility, that's this guy, and plugging in the numbers now, and you get, sure enough, it is 1. Next, you're asked to calculate the pressure at the azeotrope for the above system. So we calculate the pressure this way, summing up the partial pressures. Plugging in the numbers, we get 0.698 bar. Next, you're asked to calculate the vapor mole fraction Y1 at x1 equal 0.35. And this is a little bit more complicated because now we have to, as a first step, calculate the pressure, because it's not going to be the same as the pressure at the azeotrope. It's going to be the pressure corresponding to this mole fraction. So we calculate that as 0.6594 bar, and now I can calculate Y1. That's just gamma 1 x1 P1S over P. That has actually, we actually calculated that before, so we can get 0.46 approximately for that. And you're asked last year to sketch in and to label qualitatively accurate double point and dew point pressure curves for the above system on the coordinate system shown. Here's what it looks like. It's important to label them correctly. It shows the azeotrope here where the compositions are equal. Curves at mole fraction here of 0.7. This is just a little bit under 0.7 where we had calculated that total pressure. And here we have P2S and this is P1S. Any question about any of it? Okay, well, let me say something about going forward. I have nominally a quiz scheduled for Friday. That's not going to happen. What I'm going to do is give you, everybody gets a 25. And we don't have a quiz. We're a little bit short of time here. I've got a lot of stuff to cover here with respect to reaction equilibria. So Friday will be a regular lecture. So let's get started with this. Chemical reaction equilibria, our last unit. And there's some reading in the book that's actually fairly good. So let's make note of that.
See if you can turn it up a little bit.
Pretty much at the peak. I don't know why
Really? It doesn't really.
Not loud enough for you?
Yeah, it's not really even coming out.
That's now at the very
good.
top.
That's good. That's better. I think it's just.
The first thing we need to do is some bookkeeping, and that is a stoichiometric description of reacting systems. This is stuff you've seen before, but of course let's go through it so that we're all clear about it. And what we need to do is first tell us what it is that's happening with respect to some chemical reaction. And what that is what we call a stoichiometric reaction statement. And for example, we might write A plus 2B goes to 3C plus D. And what that tells us is, on a molar basis, that a mole of A will react with 2 moles of B to give us 3 moles of C and 1 mole of B. We could have written this, taken everything over to one side and written this as minus A minus 2B plus 3C plus D. And that helps us identify the coefficients that are out in front of these species labels. So we call that nu A, this would be nu B, nu C, and nu D. So nu A is -1, nu B is -2, nu C is 1, and nu D is 3, and nu D is 1. So these are the stoichiometric coefficients. And by convention, they are taken as negative for reactants and positive for products. We could generically write any reaction statement then in the following way, just in terms of stoichiometric coefficients, and here's the species labels. Now what we need to complete the description is not only what happens, but where do we start. So we need to know the initial state. And that means the initial inventory. Usually created out of some basis that you choose, some convenient basis. So I would have an Na0, and B0, and C0, and D0, and perhaps some inerts. So let's just call that Ni0. And it's an inert if its stoichiometric coefficient over here, of course, is just equal to 0. Now I can recreate the composition of the system at any subsequent time after a certain amount of reaction has occurred, and we have to have a way of designating how much of that reaction has proceeded from this initial state. And we use for that the variable xi. You have to get used to writing that squiggly thing. And that is what's called the extent of reaction. And what it is the number of moles of reaction. It's got other names too, sometimes called the reaction coordinate. And it obviously has units here of moles. So what it is a number of moles of reaction. So if I know xi by some piece of information that I've got about the system, for example, I might know how much of the A got consumed from the initial state. That would be enough information for me to calculate xi. And once I've got a value of xi, I can reconstruct the inventory of all of the other components. So Na here would be equal to Na0, let's write it in general here, plus UA times xi, or Na0 in this case, minus xi. NB would be NB0 plus nu B times xi, which would just be NB0 minus 2 xi. And C would be NC0, if I keep writing the whole thing here, that would be NC0 plus 3 xi. And D would be ND0 plus nu D times I equal ND0 plus xi. And of course for the inerts, they just stay constant, number of moles. Now by convention we can add up all of these things. So sum of all of these ni's would be equal to the sum of all the initial ni's plus the sum of all the new i's times I. And we generally abbreviate this by, I'll just write N for the total number of moles in the system at any given time is equal to the total initial number of moles at any given time. And then I'll call this sum of the stoichiometric coefficients just xi itself. And that's an important parameter. That's called the stoichiometric number for the reaction. And we can say in words what that is. That's the change in number of moles per mole of reaction. So we could work it out for this particular reaction. Let's just do it here. Psi would be equal to -1 minus 2 plus 3 plus 1 equals 1. So that would be the stoichiometric number for this particular reaction that I've written down as an example. Now, once we've got the inventory in terms of mole numbers, that's the most convenient way to have it, we can convert over to other measures of composition. In anticipating that we're going to be looking first, which we are, at gas phase reactions, let's use this to reconstruct values of y. So for example, Ya in this system at a given xi, can write that as Na over N, and that's equal to, let's just write it all out, Na0 plus nu A xi over N0 plus nu times xi. In our particular example, it looks like this. And I'll just say and so forth. You can construct now the mole fractions for any of the components. So what I've got here is a general statement. Find if I have some room for it. I have Ni is equal to nu I xi. Right, and I have a general statement for Yi then could be written as Ni0 plus nu I xi over N0 plus xi, plus nu times xi, which for my case here, well, we're not going to, I don't have to rewrite that. It's point made. So that's what it is if I have a single reaction, and that's what I've suggested here by just writing that one example. But I am often encountered with situations where I have multiple reactions. So let's take a quick look at that. So I've got a system here, it's got components A, B, C, D, and E, and of course we're talking about, it's been tacitly implied here, we're talking about systems at constant temperature and pressure. So let's say, for example, I've got two reactions. The first is the one I had before. But there's a second reaction. Two A plus D goes to 2E. Now each reaction has to have its own xi to be described. So I have now a xi1 and a xi2. And their meaning, of course, is derived just from the same thing as if I had a single reaction, so I don't need to say any more about that. But now as far as stoichiometric coefficients go, they're going to need a double subscript. So stoichiometric coefficients, because I can have the same species in different reactions. So I have, for example, nu A1 is equal to -1, but nu A2 is equal to -2. And so forth. But you see what I have here is a double subscript required for designating the stoichiometric coefficients in each of the two different reactions. Now I can reconstruct from an initial inventory or a basis, I can reconstruct the inventory at any later time. For example, Na would be Na0 plus nu A1 xi1 plus nu A2 xi2. And for the particular example that I've got up here, that would be the initial number of moles of A present minus xi1 minus 2 xi2. NB would be NB0 plus NB1 xi1 nu B2 times I2 is equal to NB0. If we look up there, we see that's minus 2 xi1, and there is no B in the second reaction, so that is the end of the story. But now if I sum them all up, let's just assume I've done that here, and I can sum this all up, I get N is equal to N0, but now I've got changes that come from two different reactions, so I need to be careful about my notation here. So here's the stoichiometric number for reaction 1, but I'm going to put the subscript here in parentheses to suggest now that is associated with the reaction 1. It isn't talking about some component 1. And that means I can construct mole fractions out of a system like this. It's going to be Na0, and if we look to now up here, so that would be minus xi1 minus 2 xi2 over my N0 stoichiometric number for the first reaction we figured out, that is plus 1. So xi1, we look for what it is. What's the stoichiometric number for the second reaction? Minus 1. So it would look like this, and I can write it out for the rest of them. So nothing big there, you just have to be orderly about the way you keep track of things. Okay, we're ready now, having done the bookkeeping, to discuss and describe chemical reaction equilibria. So what we got here is a system with some components in it. Let's let cells have A, B, C, and D. And again, to keep the example in mind, let's look at that same example reaction. That's just an example. And we recall again that this is a system at a given constant temperature and pressure. And what can happen is that it can react from its initial state. Xi can vary from 0 to some other point. And what we'd like to get is what is the equilibrium value for that Xi. That is, how far does the reaction go in order to get to an equilibrium state. And what we recall is that at constant temperature and pressure, the story is told by the Gibbs free energy, right? So we know that we seek a Gibbs free energy minimum in a state of equilibrium. So let's remind ourselves that this is a system at constant temperature and pressure. So at fixed constant temperature and pressure, so the only other thing that can really vary here is Xi. And I mean, look at how this is the parameter space and see, okay, what does that look like? Maybe it looks something like this. Now what I know is that the equilibrium point will be the point of minimum G. G seeks a minimum possible value, and of course that occurs, as I've indicated just graphically here. This is our equilibrium point. So this value would be the equilibrium value Xi here, just the Xi coordinate. And that's really what I would like to be able to express. So it's evident that what I've got here is an extremum, in other words, a local minimum. So what I know is that at equilibrium, actually properly, let's do it as a partial derivative here, just to, I know that partial of G with respect to xi at constant temperature and pressure equals 0. So that's what I'm going to build it out. Now we have to remember what this looks like. So recall that for an open system, we've got dg is equal to minus s dt plus vdp plus a summation here of partial molar gives free energies times the changes in mole numbers. Now we've set T and P 0, so these both go out, and this is what I'm left with. So if I'm going to write dg dxi, then this is what I've got. Now I recall here that Ni is equal to Ni0 plus nu I xi. So dni dxi is just equal to nu I. Okay, so that's the shape. I can plug all those in, and I recall that this whole thing must be equal to 0. So what I end up with out of this is that the summation here of the, and I'm going to now just reverse the order in which I write those. Summation of nu I mu I equal to 0. So there it is. Here's my equilibrium criterion, constant temperature and pressure. Well, let's look at what this thing is again. The shorthand notation for this is delta G Rxn. So that is the molar Gibbs free energy change of reaction. Lots of words here, was get it all down. So that is what we've designated here as the summation of the stoichiometric coefficients times the respective chemical potentials, and this is what it is equal to 0. Now, just as kind of an aside, I can write other property changes of reaction as well. Some of these are going to be of interest, some not. So I can have delta H reaction, and now what we understand that to be is the molar change in the system enthalpy per mole of reaction. And we call that the molar heat of reaction. We could possibly be interested in something like the volume change of reaction. You can think of other properties, any of the thermodynamic properties we have, I could write them and they would be the molar of reaction, whatever that property is. Turns out we're going to be pretty interested in this one, but for now this is the one we want to talk about. That is the molar Gibbs free energy change of reaction. And we want to set that thing equal to 0. So if we proceed with it, let's see how much room. Let's give myself a new page here. Did everybody get all of that before I flipped it off? Yeah.
Did you say that the properties of reaction, or the delta properties of reaction, are defined as the partial G, partial xi at constant T and P? Is that what?
That would be correct.
Okay.
Yeah. We can look up here at the format and construct these either as xi derivatives of the extensive property, or we can express them as we go here in terms of partial molar properties. Maybe that's worth doing. I could write this thing out, for example, as nu I here times, these would be partial mole enthalpies. This would be then mu I partial molar volumes, and so forth. Or we could write them like this. But this is our focus, so let's take a closer look at trying to express it further. So, go on another page then. So in order to evaluate that, to go further with the idea, because now what we want to do is use the fact that this is equal to 0 in equilibrium. That means we're going to need to focus on evaluating these chemical potentials. Now, this chemical potential, of course, is an energy quantity, so it has no absolute value. And that means we need to reckon it relative to some reference state. So if I just, let's recall that, and I write it out, then mu I can be written as mu I, and I'm going to say something about this in a moment, but for the moment I'm going to use that notation. That little circle with a line through it, it's called a plimsoll. So that would be the fugacity, whatever it is, it may have a hat on it or not, over the fugacity, it's the same as this. And what these refer to is what we call the standard state. So we have to define what we mean by a standard state. And once we do that, then I can reckon the chemical potential relative to the chemical potential that exists in that standard state. And for now, I'm going to stick with this symbol for a standard state. Eventually, we'll turn that into just a little circle, because it's going to turn out to be that the standard states refer to pure components. But for now, let's just leave it as the standard state quantity. So another definition here. We define this ratio of the fugacity over the fugacity in the corresponding standard state as the activity. So that would be the activity of component I in the system. And if I use that shorter-hand notation, this becomes mu I standard state plus RT logarithm of the activity.
Is that an A or an alpha?
Always an A. I haven't written an alpha yet. So our next order of business, let's see if I got enough space here, is the definition of these standard states. And here it's a matter of convention. And